All elements except iron contain potential energy. They're all fuel, star fuel. Might need a neutron star or a supernova to burn the trickier fuels though. Larger elements decay or fission, either by random quantum fluctuation or some encouragement like neutron bombardment or extreme gravity. Smaller elements fuse and can make way more energy, but atomic nuclei repel because they all have positive electric charge. If they approach fast enough, the nuclei overcome repulsion and fuse to release the energy. We're engineers, we're not gonna rely on stars or wait for random quantum jumps to get our energy. We want it now, and we're gonna spend big money to hire genius scientists and build monstrous machines to get it done. Recreating the conditions of a star sounds hard. Let's start with a big element that's practically begging to fission. Oh, this looks good. Let me just get these thorium impurities out of the way. Uranium, stable enough that we can mine it like a normal metal. Give it 1 neutron and it will fission, releasing up to 3 more neutrons. 1 atom is nothing, but if the neutrons cause more fissions, then we'll get 3, then 9. 40 steps later, 12 quintillion. We'll have exponential growth, and we'll use this energy to make steam and... Oh, it'll just destroy our power plant. And the neutrons released in fission don't move fast enough, so no chain reaction? Ah, 0.7% of the uranium will fission even with slower neutrons. I mean, yeah, 0.7% is small and it will be almost impossible to separate, and now it releases neutrons that are too fast, but hey, we got money and geniuses. Bring out the center. So we got here some special uranium that will sustain a fission chain reaction. To keep the neutrons close enough so they cause fission instead of flying away, we gotta form a critical mass, a big solid chunk of the stuff. Do it wrong and that mass would instantly overheat, destroying the power plant before we can react. That's because neutrons usually form directly after fission, and they move really fast so the chain reaction instantly becomes overwhelming. Like only 0.6% of neutrons are late to show up, because they're made indirectly from radioactive decay after fission. We need a lump that barely crosses the critical mass, so close that it wouldn't cross the threshold if it weren't for the delayed neutrons. So we just create a barely critical pile of uranium, then use water to slow down the neutrons and absorb heat. We add neutron-absorbing control rods which can be lowered like brakes to prevent the neutron count from spiking. Basically, we're driving a car and the gas pedal is stuck. We have brakes, but we have to cruise exactly 60 miles per hour. At 59.5 miles per hour, the engine will stall, and at 60.5 miles per hour, the car becomes a rocket and flies to the moon. Yeah, it's delicate, but we have advanced cruise control systems, it'll probably be fine. Oh, and also we should switch to molten salt because water can flash into steam and cause pressure explosions that spill uranium everywhere. And we can use excess neutrons to convert the wasted 99.3% uranium and the thorium impurities into something useful. And well, we have a first prototype and I'm done here. I'm sure someone will soon make those upgrades. I got bigger fish to catch, fusion power. We need to bring nuclei close together and smash them at high speed. With enough temperature and density, it should work. What's the temperature of a star? A few million degrees. Kinda high, but nothing some lasers and superconductors can't fix. What's the pressure? Whoa, hot plasma 10 times the density of gold? That needs insane pressure. Still possible, but it'll be short-lived and messy. Oh, and it'll take 9 billion years for the fusion to happen. Bummer. Fusion in stars create highly unstable fusion products that just fall apart immediately after forming. Stars rely on miracles to keep their unstable nuclei stuck together. That's why they live anywhere from 1 million to 1 trillion years, instead of instantly fusing all their mass at once in a giant explosion. We'll have to cheat a little and use fuels that directly fuse into stable products. One good choice is a type of hydrogen called deuterium, which contains 1 proton and 1 neutron. It makes up 0.01% of natural hydrogen. Yeah, so it's super abundant and easy to get. There's also a type of hydrogen with 2 neutrons called tritium. It's kinda unstable and doesn't exist naturally. Oh, the neutrons in water in our nuclear power plant already made tritium by accident. Neat. It turns out that fusing deuterium with tritium is our best bet. We're still gonna need monstrous devices though. Method 1. We use magnets to create a ring of hot hydrogen plasma. This is the method the giant fusion donuts use. The power plant generates continuous power, and we can maintain the plasma pretty efficiently with electricity. But densities are low, so we need extreme temperatures and really big donuts to make enough fusion to be worth. Also, a lot of fusion power escapes as X-rays and infrared instead of being recycled to heat up the plasma. Method 2. We fire max-powered lasers on a small hydrogen pellet in all directions to make it implode. This achieves extreme densities and the shockwave sparks fusion at the center. Then the energy released is reabsorbed as heat and the fusion sustains itself. But lasers only convert like 1% of electric energy into light, so the pellet's gotta release 100 times more energy to be worth burning. That's actually possible, but the pellet has to be compressed really symmetrically and really violently and really efficiently. Psst. Actually, we already have fusion power. Just follow me to this top secret lab in New Mexico where I can tell you more about that.
Alright, so this lab doesn't care about creating electricity. We just wanted raw power to make bombs that, fight alien motherships and deflect killer asteroids.
Why not just throw a bunch of the uranium, the 0.7% rare kind, at the aliens, enough to make several times the critical mass? Well, it will react, but not that much. We may as well throw a normal grenade. You see, nuclear reactions are very fast. Anything else we do is too slow. The moment a chain reaction begins, we have an explosion that breaks the fuel apart and makes it not critical anymore. Since uranium is unstable, there's also individual fissions happening at random times. The randomly thrown uranium will probably produce spontaneous fission when the lump is not as ready as we wished, creating nothing more than a wave of heat and some pretty blue lights as it falls apart and leaves the aliens disappointed. Random fissions happen maybe 100 times a second inside a critical mass of uranium. That's pretty frequent, but we can do a lot in 1/100th of a second. A good GPU can render one frame of a high-spec PC game and paint 8 million pixels to a 4K screen 100 times a second. Firing a uranium bullet into a uranium target with gunpowder is fast enough. That method was used in the little boy bomb dropped on Japan in World War II. Even there, less than 2% gets burned before the fuel breaks apart, because the forces are so strong that even with exponential growth there's not enough time to get more rounds of fission. The 0.7% rare kind of uranium is also pretty expensive to obtain. If just 1 or 2 bombs are needed to make a point, then that's fine. But what if we were one of 2 rivaling world powers and needed to make a bigger point? We'll need a cheaper fuel so we can make more bombs, a heavy shield around the fuel to make it fission for longer, and faster exponential growth to get more fissions before the bomb disassembles itself. All of this is achieved by using high explosives to compress a plutonium sphere to high density. The critical mass is smaller when density is higher, so shrinking a sphere of implosion can push it to 4 times the critical mass or more with less matter. A shrinking sphere is easier to shield than a moving bullet. Plutonium is cheaper because it's produced rapidly inside a nuclear reactor. Random fissions happen thousands of times more often in plutonium than uranium, but the high explosives do the job thousands of times faster than the gun design, so plutonium still works. This method is used in the Fat Man bomb dropped on Japan in World War II, and is probably the design used in all warheads today. None of this works for fusion, which needs a ton of heat and pressure to get started. Wait. A nuclear explosion easily creates star-like conditions. The most common bomb today, the Ulam-Teller thermonuclear warhead, contains a whole fission bomb, the primary, and a cylinder containing lithium and deuterium fuel, the secondary. The neutrons from the primary produces tritium from the lithium. The whole cylinder, containing deuterium and now tritium, is bathed in X-rays from the primary and its surface vaporizes. The momentum from the vaporization compresses the cylinder. Plutonium is put in the center of the cylinder so it fissions at the right time to start fusion when the hydrogen density is highest. If the hydrogen heats up early, it'll expand and resist compression. To prevent the literal atomic bomb right next door from toasting the hydrogen, the cylinder is heavily shielded. The shielding is made of uranium just so that the neutrons released from fusion adds some extra fission as a bit of icing on top. Actually, that part adds more energy than the fusion itself. Yeah, like every part of the bomb explodes and the whole thing adds up to a few hundred little boys and fat men. If our goal is to become the destroyer of worlds, then this is hopefully enough. Not really looking forward to whipping out black holes or antimatter missiles anytime soon.